Hi, this lesson is about using trigonometric identities to simplify expressions and prove equations. So the most fundamental of our trigonometric identities are those that you see right here. So we know that the sine of theta is equal to 1 over cosecant of theta, where theta is any angle within the domain of the functions. Also, if I'm going across, cosine of theta is equal to 1 over secant of theta. Tangent of theta is equal to 1 over cotangent of theta. And because those three are true, the reciprocal relationships also exist. Cosecant of theta is equal to 1 over sine of theta. Secant of theta is equal to 1 over cosine of theta. And cotangent of theta is equal to 1 over tangent of theta. In addition, you're going to want to make sure you know that the tangent of theta is equal to sine of theta over cosine of theta. And because tangent and cotangent are reciprocals of each other, cotangent of theta is cosine of theta over sine of theta. So all those should be memorized. In addition, make sure the Pythagorean identities are memorized. There are three. The first one is that cosine squared of x plus sine squared of x equals 1. The second one is that 1 plus tangent squared of x equals secant squared of x. And the third one is that cotangent squared of x plus 1 equals cosecant squared of x. Okay, so if you ever have trouble remembering all of these, as long as you remember the first one, you can easily derive the second and the third. So you can derive the second one by dividing everything in the first identity by cosine squared of x. And if you do that, you get that cosine squared of x over cosine squared of x. We get sine squared of x over cosine squared of x, and we get 1 over cosine squared of x. Well, we know that cosine squared over cosine squared, well, that's where the 1 comes from, right here. Sine squared of x over cosine squared of x, remember that's equal to tangent, so that's where tangent squared comes from. And 1 over cosine, we know that 1 over cosine is equal to secant, so that's why we get secant squared after the equal sign in that identity. Similarly, you can you can derive the third one from the first one by dividing everything by sine squared of x. So if you get cosine squared, the first term, divided by sine squared of x, plus sine squared of x over sine squared of x equals 1 over sine squared of x. Okay, so cosine squared over sine squared, well, we know that's equal to cotangent. So we know that that's where cotangent squared comes from. We know that sine squared of x over sine squared of x, well, that's just 1. That's where you get the second term from. And 1 over sine of x is equal to cosecant, so 1 over sine squared is cosecant squared of x. So you can easily derive the second and third Pythagorean identity from the first one. All right, so let's use this information in order to simplify an expression. So this one says to write the trigonometric expression in terms of sine and cosine, then simplify. And the expression is secant of theta over cosecant of theta. So first we rewrite secant of theta as 1 over cosine, that's by definition, and cosecant is written as 1 over sine, also by definition. Okay, but that means that I have one fraction divided by another fraction, and when you divide fractions, it's the same as multiplying the first fraction by the reciprocal of the second. So that's what you see here, 1 over cosine theta times sine theta over 1. But when you multiply those two fractions, you get sine of theta over cosine of theta, and again, by definition, sine of theta over cosine of theta is tangent of theta. All right, so let's do another one. So we have sine to the fourth of a minus cosine to the fourth of a. plus cosine squared of A. And the directions just say to simplify. All right, so before we do anything, I want you to just notice that the notation here is important for you to understand. Sine squared of A, or sine to any power of A, that's the same as the sine of A squared. So in other words, if you had a value for A, the angle, you would first evaluate the sine of that angle and then square the result. But the notation is not the same as what you see here. The sine squared of A is not the same as the sine of A squared, where just the A is being squared. So that's just some notation to keep in mind so you don't get confused. But in terms of simplifying, we're going to be treating the first two terms as the difference of perfect squares. That's what they are, and factoring them. So here is a reminder of what the difference of perfect squares formula looks like. If you have a squared minus b squared, the factors are a plus b and a minus b, where a and b are the square roots of a squared and b squared, respectively. Okay, but we have something raised to the fourth power. So what you see here is the formula for the difference of perfect squares, where your perfect squares are raised to the fourth power. So here I have a squared plus b squared times a squared minus b squared. So we're going to apply this second formula here on the right to my expression. So when you factor the first two terms as the difference of perfect squares, you get this right here. The sine squared of a plus the cosine squared of a times sine squared of a minus cosine squared of a. And then outside of those two factors is the last term, which just gets brought down. That's cosine squared of a. Okay, but we can make a substitution here because the first binomial, this one right here, is one of the Pythagorean identities. In fact, it's the first one right here. So I have the sine squared of an angle plus the cosine squared of an angle. Well, we know that's equal to 1. So you replace 1 in the second line here. So I get 1 times sine squared of a minus cosine squared of a plus cosine squared of a. Well, when you distribute the first binomial by 1, you end up with 3 terms, and minus cosine squared of a and cosine squared of a, well, they cancel each other out, and you're left with just the sine squared of a. All right, so here we're going to prove an identity. So an identity means that the left side and the right side are equal, and proving it means that we want to make one side look like the other side. So we want to prove that the tangent of y over the sine of y is equal to the secant of y. So I'm going to manipulate the left side of this, which is the more complex side, until it looks like the right side. So the first thing I'm going to do is rewrite tangent in terms of sine and cosine. So tangent of y is sine of y over cosine of y. And then I'm also going to rewrite my division bar here in this way as divided by sine of y. Okay, so again, as I mentioned before, dividing is the same as multiplying by the reciprocal. So I skipped a step here, so let me just write it out for you. That means that when you change division to multiplication, you get sine of y over cosine of y times 1 over sine of y. So the sine of y's cancel, which leaves you with just 1 over cosine of y, which is right here, and 1 over cosine of y is secant. So secant of y equals secant of y, and you have proven that the identity is true. Okay, let's do another proving problem. Prove that cotangent of theta times secant of theta equals cosecant of theta. So again, I'm going to rewrite everything possible on the left in terms of sine and or cosine. So cotangent is cosine over sine, which you see here, and secant is 1 over cosine, which you see here. But then the cosines cancel, and you're left with just 1 over sine, And 1 over sine by definition is equal to cosecant. So the left side equals the right side, and you're done. Okay, next example is very similar. We want to prove that cosine of x tangent of x equals sine of x. So first rewrite the left side in terms of sine and or cosine. So the only thing you can really change is tangent, and tangent is sine over cosine. So I have cosine of x times sine of x over cosine of x, and we want to make sure that equals sine of x. Well, this one simplifies pretty quickly because the cosines cancel, and you're left with the left side and the right side are both equal to sine. All right, this next one is a little bit more complex. Directions are different as well. We want to simplify cosine of x minus cosine cubed of x over sine of x minus sine cubed of x. And the result will be one of the 6 trigonometric functions. So the first thing I did was factor. So I factored out a cosine of x from the numerator. And here I factored a sine of x from the denominator. So that leaves me with cosine of x times 1 minus sine squared of x, and sine of x times 1 minus sine squared of x in the denominator. Okay, but then I made a substitution. From the second line to the third line, 1 minus cosine squared became sine squared, and 1 minus sine squared of x became cosine squared. But how did that happen? Well, that work is right here. I used the first Pythagorean identity. So the first Pythagorean identity says that cosine squared of x plus sine squared of x equals 1. If I subtract cosine squared of x from both sides, you get that the sine squared of x equals 1 minus cosine squared of x. So that sine squared gets substituted here in this line. Similarly, you take cosine squared of x plus sine squared of x. This time subtract sine squared, and you get cosine squared is equal to 1 minus sine squared, and that gets substituted into the denominator. All right, but when you do that, some factors cancel. So a cosine in the numerator cancels with 1 in the denominator, and a sine in the denominator cancels with 1 in the numerator. So your final answer, or your almost final answer, is sine of x over cosine of x, but we know that that is equal to tangent by definition. All right, here's another example. Same instructions. We want to simplify sine of x times tangent of x plus cotangent of x so that your result is one of the 6 trigonometric functions. So from the first step to the second step, I rewrote tangent in terms of sine of x over cosine of x, and cotangent as cosine of x over sine of x. So from the second line to the third line, I distributed sine across the parentheses. So I have sine squared of x over cosine of x plus sine of x cosine of x over sine of x. But that leaves me with 2 expressions with different denominators. And so my LCD is the product of cosine of x, sine of x. The first expression has to get multiplied by sine of x, and the second one by cosine. So when you multiply the first one by sine of x on the top and the bottom, you get sine cubed of x over cosine of x sine of x. And when you multiply the second expression by cosine, you get sine of x cosine squared of x over sine of x cosine of x. All right, but then here I'm left with 2 expressions in the numerator with a common factor of sine. So I'm factoring it out here. So I have sine of x times sine squared of x plus cosine squared of x over my denominator. But we know that sine squared of x plus cosine squared of x equals 1. So your numerator is just sine of x. And so sine of x over cosine of x sine of x, well, the sines will cancel. You're left with 1 over cosine of x, which is the same as secant of x. Okay. So here's a different one, different instructions. We want to show that the expression cotangent of y, cosecant of y, secant of y, minus cosecant of y, cosine of y, cotangent of y, has a constant value. And what that means is it should all simplify down to a single number. So, as I mentioned in the earlier problems, everything that you can rewrite in terms of sine and or cosine, you should. So cotangent of y becomes cosine of y over sine of y. Cosecant becomes 1 over sine of y. Secant becomes 1 over cosine of y. Minus, and then cosecant of y is 1 over sine. Cosine of y stays the same, and cotangent of y is cosine of y over sine of y. All right, so once everything is written out here as one product minus another product, some things will cancel. So the cosine of y here cancels with the one here. Nothing cancels in the second product. But the first one becomes 1 over sine squared of y. The second one becomes 1 minus cosine squared of y, and they both have a common denominator of sine squared of y, which means you can write it as a single expression. But similar to what I explained before, we know that 1 minus cosine squared of y, if you manipulate the first Pythagorean theorem, well, that numerator equals sine squared of y, and therefore sine squared of y over sine squared of y, well, they cancel each other out, and the whole thing is equal to 1. Okay, here's another. We want to prove that the tangent squared of x minus the secant squared of x over the cosecant squared of x equals 0. All right, so we need to manipulate the left side of the expression. I'm going to take a slightly different approach. I'm not going to rewrite everything in terms of sine and cosine. I'm actually going to work with the second expression, the secant squared and the cosecant squared. So secant squared of x, well, that's the same as 1 over cosine squared. And 1 over cosecant squared of x, well, that's the same as sine squared. So when you multiply the second expression, you get sine squared of x over cosine squared of x. But we know that sine squared over cosine squared is just tangent squared of x. So the first term, tangent squared of x, minus the second term, which is also tangent squared of x, well, that's just equal to 0. Left side equals the right side. So you're done. All right, here's another proving problem. We have the sine squared of t over the cosine of t plus the cosine of t equals secant of t. So again, we'll manipulate the left side until it looks like the right side. So the first thing I did was to get a common denominator for the two terms on the left, which is cosine of t. So the second expression has to get multiplied by cosine of t over cosine of t. So that leaves me with this line here, sine squared of t over cosine of t plus cosine squared of t over cosine of t. Is that equal to secant of t? So rewriting it as a single expression leaves me with sine of t squared, sine squared of t plus cosine squared of t over cosine of t, but we know that that's the Pythagorean identity equal to 1, and 1 over cosine of t, well, that's equal to secant of t. Left side equals the right side, so again, you have proven the identity. Okay, here's another proving problem. We want to prove that secant of theta cosine theta minus cosine squared of theta equals sine squared of theta. So similar to the other problems, I first rewrote the left side in terms of cosine in this case. Secant gets rewritten as 1 over cosine. But when you do that, the cosines here will cancel each other out. So you're left with 1 minus cosine squared. But again, that's one of the Pythagorean identities just written in a different way. 1 minus cosine squared is equivalent to sine squared of theta. So the left side equals the right side. Identity has been proven. Okay, here's another one. We want to prove that the cosine squared of x minus 1 over cosecant squared of x equals cosine squared of x. So this is cosecant squared. I might have said cosine earlier. All right, so this time I'm going to be using the third Pythagorean identity, which said that 1 plus cotangent squared of x equals cosecant squared of x. Okay, and notice that here I have cosecant squared of x minus 1. So if I subtract both sides by 1, you'll get cosecant squared of x minus 1 on the right. So that's why I replaced that numerator with cotangent squared. Okay, so now my left side will get rewritten in terms of something else. So my cotangent gets rewritten as cosine squared of x over sine squared of x. And 1 over cosecant gets written as sine squared of x. The sine squareds cancel in that step right here. So you're left with cosine squared of x equals cosine squared of x. So the identity has been proven. Okay, here's another one with just a constant on the right. We have 2 tangent squared of x plus 2 over 4 secant squared of x. We want to prove that that's equal to a half. Okay, so in the numerator, first I factored out a 2, which is what you see here. So that's 2 tangent squared of x plus 1. And that one also should remind you of one of the Pythagorean identities. The identity says that the tangent squared of x plus 1 equals the secant squared of x. So from the second line to the third line, I replaced tangent squared of x plus 1 by secant squared. But that means that I have 2 secant squared over 4 secant squared. The secant squareds cancel each other out, so you're left with 2 over 4, and when you simplify that, you get a half. So the left side equals the right side, so you have proven the identity. So now you should be able to do the homework for 7.1. Good luck.